All right, so now that you have a good understanding of the insulin release from the beta cell, we're going to kind of add to that with a little bit more detail. So the subsequent slides are going to seem a little bit like a review, but with just a little bit more detail. Because we're going to talk about some of the more cellular control of insulin release. So how blood sugar levels affect insulin's release. So again, a little bit more detail about the things we've already talked about. So again, this is the beta cell, just to orient you here. We have your glucose, the GLUT2, the glucokinase. Here is the production of ATP. Here is the ATP-sensitive potassium channels. And then you have, excuse me, then you have the voltage-gated dependent calcium channels. And finally, the insulin granules, the secretory vesicles that contain insulin. So it's just the same thing we've already talked about, but we're going to talk a little bit more about kind of the fine tuning of how insulin is released based on your blood sugar level. So the first thing is to understand that the beta cell's primary function is to correlate release of insulin with changes in blood glucose concentration. Because these cells must have a sensitive glucose measuring device, otherwise insulin would be released continuously even when blood sugar levels are low, and that could cause someone to fall into a coma or even worse. So the way that this fine-tuning of controlling insulin release starts with the GLUT2 and glucokinase. These are going to be considered sensors of glucose, but they're only going to be activated when glucose levels are high. In other words, they have a low affinity for glucose, which basically means that they do not activate when glucose levels are low, and therefore they'll be closed or inactivated. So in other words, only when glucose levels rise above 100 milligrams per deciliter in a normal individual. So simply what you would see after a meal, will GLUT2 be activated and turned on. But so after a meal, your glucose levels rise, GLUT2 will be activated or opened up to allow glucose to come into the cell. So transport of glucose into the beta cell is rapid, but only when the blood glucose concentration exceeds post-meal levels. So in other words, when after a meal, blood sugar levels rise, GLUT2 is turned on or opens up, and glucose is able to enter. But as glucose levels start to drop below 100, GLUT2 is going to be turned off or closed because they have a low affinity. So when glucose levels are low, GLUT2 and glucose don't talk to each other. Likewise, glucokinase is the same way as GLUT2, that it has a low affinity for glucose. So it doesn't like glucose when blood sugar or blood glucose levels are low. So anything below 100, glucokinase is not turned on. It's only after a meal when glucose levels rise above 100 that glucokinase is activated. Now you're probably thinking, well, what about a type 2 diabetic that has glucose values that are greater than 100? Well, they're going to have a set point. Let's say it might be 140, might be their set point. And that is only after it reaches in that diabetic, since they have higher fasting blood glucose levels, it's only after above 140 that GLUT2 is going to be turned on or opened up. Okay, so, but in a healthy individual, a normal individual, the blood glucose levels below 100, GLUT2 and glucokinase are going to be closed and deactivated. It's only when glucose levels rise post-meal that they're going to be activated and to start the process of insulin release. And it makes sense because you wouldn't want to have insulin to be released when your blood sugar is already low, because that's only going to drive your glucose levels even lower. So both uptake of glucose by the beta cell and initiation of glycolysis closely follow blood glucose levels. They respond to increases in blood glucose found immediately after food intake, resulting in rapid uptake and metabolism of glucose, but which is rather sluggish at the lower glucose levels found between meals. So in other words, as mentioned, GLU2, glucokinase are only activated when after a meal the blood sugar rises above 100. And it makes sense because you wouldn't want glucose to be, or insulin to be released when it's already low, only when glucose levels are high. What about the special ATP potassium channels? They're also known as Kerr 6.2 channels. And these channels are basically, you have a channel that's actually a protein called Kerr 6.2, and then you also have a protein that wraps around it called SIR1. The SIR1 is the one that tends to respond to changes in ATP concentration within the beta cell. So this is going to be a regulatory cell. The SIR complex is going to be the one that's going to regulate whether or not ATP is high enough in the beta cell, and if it's high enough, that's going to cause the Kerr 6.2 channel itself to actually open up, allowing potassium to escape. When ATP levels are high, that's when the Kerr 6.2 channels are going to open up, close to trap potassium in the cell. So at resting membrane, so in between the meals, when your blood sugar level is below 100, these potassium channels, this ATP sensitive potassium channel, is going to be open, allowing potassium to escape. It's only upon after a meal, when glucose comes into the cell and ATP is made and it rises, that it's going to be recognized by this channel, and that's going to close the potassium channel, and therefore trapping potassium inside the beta cell. And normally during rest, that cell membrane of the beta cell is going to be about minus 60 millivolts. But as we talked about before, when you trap potassium in the cell, that's going to cause depolarization. So let's walk through this. So when you have an increase in blood glucose, that's going to cause an increase in ATP to be formed in the beta cell, and that's going to be recognized by these special channels, the Kerr 6.2 and the SIR1. Well, as a result, they're going to then close off. The Kerr 6.2 channel is going to close, preventing potassium from escaping the beta cell. As a result, potassium with its positive charge is going to accumulate. That's going to cause depolarization of the cell membrane, which basically means the cell membrane is now going to become less negative. It's going to move from minus 60 microvolts or millivolts to minus 40. As a result, then that wave of depolarization is going to make its way down the cell membrane. So this is kind of the overview of the role of how that ATP sensitive potassium channel works. It's going to be closed in between meals. It's going to be open. Yes, it's going to be closed in between meals, but it's going to close right after a meal. Okay. Well, the final step, as we talked about, has to deal with the voltage-gated calcium channels. Well, they're going to be closed at minus 60 millivolts, but once that wave of depolarization moves down and it reaches that, and it becomes minus 40 millivolt charge, makes its way to the voltage-gated calcium channel, that's going to cause that voltage-gated calcium channel to open, and calcium is able to enter the beta cell. And then that calcium is used to help move along the insulin inside these storage vesicles from the inside of the beta cell to the cell membrane where they are released. Okay, so this right here is kind of a little bit more detail of what we've already talked about. So it should be a little bit more of a review, but just gives you a little bit more of the fine tuning as to how blood sugar is associated with the release of insulin. Now let's take a practice. Let's do some practice. Describe what the response would be, open or closed, activated or not activated, for GLUT2 transporter, glucokinase, and the Kerr 6.2 potassium channel, and the voltage-gated calcium channel. The voltage-gated calcium channel when blood glucose is either 60 milligrams per deciliter or 150 milligrams per deciliter. So this right here is going to be in between meals, and this is going to be after a meal. And this is going to be in a normal individual. So take a moment, pause the video, and make a table and decide which is going to be, when are these going to be activated and or open or closed based on the blood sugar levels. All right, let's go ahead and check to see how much, review how much you got right here. So here again is the question, and here's the two levels of blood sugar, and here's our pathway or figure that shows the release of insulin from the pancreas. And so let's start out. We have, again, we talked about GLUT2, glucokinase, the ATP sensitive potassium channel, and then the voltage-gated calcium channel. So what happens at 60 milligrams per deciliter? Well, as you recall, with the lowering of glucose, that's going to cause these GLUT2 channels to close, and as a result, glucokinase is also going to be not activated. Well, when these are not activated at low glucose levels, that's going to cause these ATP-sensitive potassium channels to remain open, allowing potassium to escape. As a result, you're not going to have a depolarization of this cell membrane, and therefore, without depolarization, the voltage-gated calcium channels will remain closed. Without calcium entering the beta cell, the insulin inside these vesicles will remain in the middle of the beta cell, and therefore insulin is not released. And that's what happens, and that would make sense because when you have a level of 60 milligrams per deciliter, that's going to be in between meals when your blood sugar is already low and you have no need for your insulin to be released. Now, in contrast, what happens after a meal when your blood sugar rises, let's say, to 150 milligrams per deciliter? Well, that's going to cause the GLUT2 to be activated. They're going to open up, allowing glucose to enter the cell. That's going to allow the glucose is going to undergo glycolysis, forming more ATP. And as a result, with increase in ATP, that's going to close these ATP-sensitive potassium channels. With the rise in potassium, the positive charge inside the beta cell, that's going to cause the depolarization, going from a minus 60 millivolts to a minus 40 millivolts. Well, that at minus 40 millivolts, the voltage-gated calcium channels will open, calcium will enter, allowing for the release of, or the movement of these insulin storage vesicles to move from the middle of the beta cell to the cell membrane to release insulin. So this should be a good overview. Again, review this, make sure you understand the opening, when they're going to be open, when they're going to be closed, based on the blood sugar level. Now, we talked about the release of insulin. Well, there's actually two phases of insulin release that we should talk about. We have a fast phase, a phase 1, that's going to require ATP and calcium, in which granules in the readily released pool that's right by the cell membrane, the docked pool. So think about it here. This is right here. Here's the first phase. Here's this beta cell membrane. Here is the insulin inside these storage vesicles. Some of these are going to be readily released pool right next to the cell membrane. They're going to require calcium and some ATP. This phase of insulin is going to amount to about 5% of the total released after a meal, but it's an important phase 1 of insulin release. Well, then you have a slow secondary phase that requires ATP, and these are going to move from the reserve pool. So the reserve pool here's the reserve pool of insulin in these storage vesicles that are going to be away from the cell membrane, more in the middle of the beta cell. And they're going to take a little bit longer to make their way to the cell membrane. So they're going to make their way and they're going to dock, and they're going to then, with the help of calcium, they're going to finally be released. So this is the phase 2. This phase 2 accounts for the majority, about 90 to 95% of insulin released after a meal. Interesting to note, so the docking energy of the granules are part of the slow second phase. The slow phase is the major contributor to insulin release. About 90 to 95% of insulin released after a meal is due to this slower secondary pool that has made it, that kind of hangs out in the middle of the beta cell and has to make its way to the cell membrane. Also note, the maximal quantities of insulin are released after about 60 minutes following a meal. So it takes about 60 minutes for this process for the insulin to finally reach maximum to help bring down the glucose levels. Well, again, what's the importance of these phase 1 and phase 2? Well, let's look here at this figure. Here we have this blue line is the insulin levels, and we have phase 1 here with this big spike, and then we have phase 2 that slowly rises in insulin level. Representing this dotted line and then this dark line here is the blood glucose level. So assuming you have a meal, your blood glucose levels will rise, and they're going to stay at level, and then they're going to eventually go down as insulin levels rise. So the question is what's the importance of this phase 1? Well, phase 1 is important because this bolus, think of this large bolus of insulin that from this immediate readily docked granules is going to be released into the blood, and its job is to keep glucose levels from rising too high. At the same time, as you see the phase 1 starts to drop, phase 2 kicks in. Well, it gives this phase 1 allows time for phase 2 for this reserve pool to make its way to the cell membrane and to be released. And you can see finally over time, phase 2 insulin is released, and the blood glucose levels will go down. So this phase 1 is important because this bolus prevents glucose from rising too high, and it provides time for phase 2 to kick in and increase blood sugar level or insulin levels. Important to note, phase 1 level or phase 1 tends to be the first phase that goes in developing of type 2 diabetes. So you tend to lose that effect of this phase 1 initial bolus. So if you think back to a previous slide that we talked about the 24-hour plasma glucose, you notice again in a healthy individual, you have these sharp spikes of glucose before coming down. Well, they have both phase 1 and phase 2 that are active. However, in a type 2 diabetic, it's lost that bolus, that phase 1. So insulin levels, it takes a while for insulin levels to build up in the blood. As a result, glucose levels will rise and they'll stay elevated for quite some time with this plateau phase before returning back down. So that's why you have this plateauing effect, because type 2 diabetics have lost that phase 1, that initial bolus of insulin, whereas in a healthy individual, they both have phase 1 and phase 2. So insulin secretion from beta cells occurs very rapidly after glucose ingestion and is reported to occur with precise and biphasic kinetics. Biphasic meaning phase 1 and phase 2. So insulin secretion is dependent on ATP generation and a rise in intracellular calcium. So those 7 steps that we've talked about with calcium entering into the beta cell. And phase 2 is dependent on mitochondrial metabolism, so the making of ATP, and a rise in the calcium levels inside the beta cell to help with the movement. The calcium help moves those reserve pool from the middle of the beta cell to the cell membrane. So again, this is just the release. Pancreas is released kind of in pulses. Again, it's going to be released, pulse 1, pulse 2, and that insulin is going to then make its way to the liver and throughout the rest of the body. Again, just to reiterate, we have insulin in the mesenteric vein. That's where it's going to be released. just to kind of reiterate. And then here we have, again, what it looks like, again, the islets of Langerhans, where we have the beta, or the insulin that's going to be stored here in the islets of Langerhans. And then the white lines here are just the blood vessels. All right, so how it's degraded? It's important in order for the blood sugar to be regulated quickly. Insulin's going to have to be broken down pretty quickly. Well, it's done so through an enzyme called insulinase. Again, anything that ends in an ASE is an enzyme that breaks something down. In this case, insulin. Insulinase is found in the liver and the kidneys, and it breaks down insulin circulating in the plasma. And as a result, insulin has a half-life, or a functioning time in the blood, of only about 6 minutes in the blood. Well, why is this 6 minutes important? Well, this short duration of action by insulin allows for rapid changes in the circulating levels of insulin, and therefore the control of blood sugar. If insulin lasted a very long time in the blood, you could have glucose levels would drop too much, and therefore you would have people would go into a coma, or even worse. So this rapid half-life, the short half-life, allows for the body to control the blood sugar more fine-tunedly than if the half-life functioning of insulin was much longer. All right, so we have some review questions here that I would recommend that you do. So make sure that you do these, and we're going to pause the video, write the answer to these using the notes from lesson 4 from this section, and then we'll practice them. We'll go over them. All right, so let's go ahead and let's review these questions. What is the role of calcium in insulin release? Well, as we know, the role of calcium is used to help with the movement of the storage vesicles from the middle of the beta cell to the cell membrane. Number 2, list what happens in each of these 7 steps of insulin secretion when glucose values drop to below 80 milligrams per deciliter. So when would these 7 reverse steps occur? Well, they would occur in between meals. So when would 80 milligrams per deciliter? So in between meals is when your blood sugar levels would drop below 100 and be in your normal resting in between meal levels. So what would happen to these 7 steps? Well, you would have a decrease in blood sugar levels that would cause a GLUT tube to close, preventing glucose from entering. As a result, there would be no glucose to undergo glycolysis to make ATP. So therefore, you would have a decrease in ATP levels. This reduction in ATP in the beta cell would cause the ATP-sensitive potassium channels to open. They would stay open, allowing potassium to escape. Potassium then would not build up, and you would not have a depolarization of the cell membrane. It would remain at minus 60 millivolts. As a result, without depolarization, the voltage-gated calcium channels would close or remain closed. Calcium would not be able to enter, and therefore you would have these storage vesicles would remain in the middle of the beta cell and not be able to move to the cell membrane to release insulin. And that makes sense. You would basically be turning off these 7 steps, which would make sense because you wouldn't want to have insulin to be released when your blood sugar is already low to begin with. So what happens to insulin secretion during exercise? Well, insulin secretion is going to decrease during exercise. So the question is then, how does glucose get into the cell during exercise if insulin levels are low? Well, the way it occurs is through muscle contraction. And what happens is muscle contraction through movement allows for glucose to get into the cell independent of insulin. So it would make sense that since your muscles are contracting, glucose is able to come into the cell. You wouldn't want insulin to also be circulating because that would drive down your blood sugar too much. But muscle contraction activates a process in the skeletal muscles that allows glucose to enter the cell without insulin. So muscle contraction is what causes glucose to get into the cell during exercise. And that's just depicted here. And you don't need to really know this at this point, but just know that it has to do with muscle contraction. All right, so this concludes this section of lesson 4. Make sure that you have a good understanding about the various release of insulin from the beta cell and the fine tuning that we talked about before we go on. So to the next part of this lesson, which is going to do now, what happens that insulin when it makes its way to the tissues of the body.